So this is a pretty typical problem you would see in a gas laws unit. The problem reads, a gas with a volume of 3.00 times 10 to the second power milliliters at 150 degrees Celsius is heated until its volume is 6.00 times 10 to the second milliliters at a constant pressure. To what temperature was this gas heated? So basically we have a gas, it's in a certain volume, and then it gets heated up, and we want to see what the new volume is, or we want to see what the new temperature is, because the volume has changed. I always like to start my problems, my gas law problems, with this little chart where I have P, V, T, N down the center, pressure, volume, temperature, and the number of moles, which is also the amount of gas. And we have a 1 to represent the initial conditions, how the problem starts, and a 2 to represent the final conditions after the change happens. In this case, the change is going to be that the volume increases. It's a really good idea that you start, if you haven't already, recognizing what unit goes along with the variable. And when I see milliliters, I know that's a unit for volume. So I'm going to take this 3.00 times 10 to the second milliliters, and I'll just place this into my chart under the V1 section. I see degrees Celsius for another value, and degrees Celsius tells me we're talking about a temperature, so I'm going to place that number into my chart. Finally, I do see a number that represents the other volume because we do have a container, it's being heated and the volume expands, and that is going to be represented in the V2 section. We see a key word here, a key phrase, at constant pressure, and what we can do is we can just cancel that out of the equation. And you did see the T2 pop up because it says to what temperature was this gas heated, and that's our unknown variable, that's our X. In this case, we actually don't have any information about moles, and it doesn't say that the number of moles is constant or the amount of gas is constant, but it's okay to assume that we can remove that from the problem as well, because if this is basically a closed container, it's sealed tight. Yes, the volume is changing, the container is getting larger and smaller, but the amount of gas itself, the moles of gas, is not changing. All right, so a few things before we begin with a formula. We always want to make sure our units for volume match up. Milliliters, milliliters, check, we can move on. We always want to make sure our temperature is in Kelvin. Since I see Celsius here, we need to use the back of our periodic tables, or just our knowledge, and know that whenever we have Celsius, you have to add 273. So 150 plus 273, and that comes out to 423. Okay, now we can keep moving on with our problem. Now, I know some of you guys get a little scared when you see scientific notation. I do have a tutorial on YouTube for scientific notation for you to view, but if it makes you more comfortable, you can do one of two things. One, you can take it out of scientific notation by moving the decimal place to the right 2 times and just converting this to a normal long form number 300. The other thing you can do is just remember when you type it in your calculator, it's just 3.00 times, 3.00, hit that EE button and then 2, and it works like a normal number. This just means 300, this just means 600. It's just the scientific notation form of it. Okay, so now let's get back to the problem. Since we see numbers on both sides of the equation, as you look at the back of your periodic table, under the section that says behavior of gases, I've told you in a previous tutorial to only focus on the first 3 formulas. Only focus on the first 3. Now the first, if you're looking at the back of the periodic table, under the behavior of gases section, the first formula only has pressures, which this obviously doesn't even have a pressure in the problem. The second formula is PV equals nRT. That's only one pressure, one volume, one temperature, and we actually have 2 volumes involved, and we're dealing with 2 temperature situations. And that leaves us with the third formula. This is the combined gas law. Now, we always start off with this formula, not the 3 formulas listed under this one on the back of your periodic table, because we definitely want to know how to manipulate this one to the best, that would help us with the problem that we're dealing with. Now, since P and N are crossed out of our chart, we go ahead and cross those out of our formula too, and we're left with V1 over T1 equals V2 over T2. This is actually Charles's law. Next thing we're going to do, we're going to plug in our numbers. There is V1 in our numerator position. We have T2, we have V2, and we have T2. Sorry, did I say T2 earlier? I meant T1. So V1 over T1 equals V2 over T2. All right, this is what we have. Now, go ahead and take a moment, hit pause, try to solve this out, and then we'll check your algebra together. But go ahead and hit pause and solve for T2. And if you're ready to continue, let's talk about the algebra. Now, in my experience, I have found that some of my students are not great at algebra. Now, like in this case, the answer you're supposed to get is 846. If you didn't get 846, you need to reevaluate your algebra. You might be doing the algebra incorrectly, so I want to show you a really easy way to solve this problem. I like to use cross multiplication because with cross multiplication, you have a less chance of messing up the algebra, and it really helps with not losing any digits through rounding and things like that. So with cross multiplication, what you want to do is you want to focus on the two crosses in this problem that kind of looks like two fractions being set equal to each other. It looks like a proportion. In this case, it actually is a proportion. Well, this is a cross and this is a cross. We're always going to start off with the cross that doesn't have the unknown variable. So we're going to start off with this cross and we're going to multiply these two numbers together. So 423 times 6.00 EE2. And then we divide by all the other numbers in the other cross. So divided by 3.00 times 10 to the second power. And when you do that, you should have 846. Now I goofed right here and I should have added another 0. And when we look at all the numbers, we see 3 sig figs, and that's why my answer's in 3 sig figs. But we need a unit in our final answer. Our temperature is always solved in Kelvin, which tells us this temperature is in Kelvin. But should you be requested to show your answer in Celsius, you just take this number, subtract 273, and you would get 573 degrees Celsius. Now remember, you can never solve a problem using Celsius. Okay, always solve it using Kelvin.